Tonight we are joined by Dr. Howard Spero. Did I get? Great, thank you. He is a professor and chairman of the Geology Department at the University of California, Davis, and director of the Stable Isotopes Laboratory. His career includes authorship on over 100 scientific publications. He is a fellow of the California Academy of Sciences, the Geological Society of America, and the American Association for the Advancement of Science. His research group focuses on the calibration and development of geochemical tools to extract novel environmental information from the shells of marine fossils in ocean sediment to reconstruct the history of Earth's past climates. So here to tell us about changing seas is Dr. Howard Spero.
My background is sort of relatively diverse. As I was saying to Barbara a few minutes ago, I had my Ph.D. in biology and then discovered a passion and I changed fields. And my postdoc became a geochemist, which sort of overnight wound up dropping me into the climate change phenomena that has been going on for the past 20 years or so. And what I want to talk to you tonight is a little bit about that. Now, I've given talks like this before, and I've had people come up to me in various places. I've been up in Nevada and elsewhere. And before I even get to talk, somebody will walk up and say, I'm not going to believe a single thing that you say. Okay, and it's kind of tough to talk about climate change or about what is going on the planet today and where we're looking at the future without at least an open mind. So I think that this is probably a little bit of a different audience than I've experienced in Nevada, but nevertheless, you know, place your opinions outside the door. And what we're going to do today is we're going to talk about the science of climate change, not whether it's going to warm up or cool down. We're going to talk about what has been going on over the past 50 million years, and we're going to take a kind of a circuitous route to get there. I want to talk a little bit about climate change 101 in the sense of how does the Earth's climate system actually operate? And talk a little bit about CO2, one of the prominent greenhouse gases on the planet today. Greenhouse gases are important. We would not be here if it wasn't for carbon dioxide and its effect on trapping heat in the atmosphere. So it's really an important component of the planet today. Many of you have probably heard about ocean acidification. They've called it the other CO2 problem, and has caused a lot of angst amongst politicians, especially those on the right, because of the fact that they see it as another thing that the scientists are rolling out. So what I want to do is I'm going to give you a little chemistry today. So for the chemophobes, I'm sorry, I apologize ahead of time. We're going to do a little bit of carbon chemistry. And what I call tales from the crypt. My field is paleoceanography. I work with marine fossils that live in the surface plankton, and when they die, their shells sink into the seafloor. And when they do, they record environmental information about the surface environment of the planet. And a lot of the research my graduate students, undergraduates, and postdocs do working to calibrate those geochemical tools to reconstruct past climates. And we're going to talk a little bit about that, and I'll give you an example of something very, very scary from 55 million years ago that's an analog for where we are today. And we'll finish up with the sort of philosophical aspects about this and perhaps how bad we'll actually see the planet get. And I'm going to leave this up to you afterwards to have an open discussion because there's a lot that you probably want to ask about. I was a program officer at the National Science Foundation for several years between 2006 and 2008. I was working in the Ocean Sciences Division, working on paleoceanography, basically making decisions on the funding of the planet, not the planet, the nation as far as the science goes. And while I was there, The Economist came out with this cover issue. And the heat is on, and needless to say, we wound up embroiled very quickly up on Capitol Hill at the National Science Foundation with the issues and the science of climate change, what's real and what's not. Come on, there you go. So let's just talk about how the Earth operates from a science perspective. Okay, the Earth is a huge heat engine. In the tropics, sunlight warms up the oceans, warms up the planet. At the poles, there's very little sunlight hitting it. Therefore, we have to figure out some way to get energy from the tropics up to the poles. And it's the atmosphere and the oceans that transport that heat north and south away from the tropical regions. Along the way, the planet's radiating heat back to space. Sunlight comes in, water absorbs heat, surface absorbs heat, reflects back to space, and it's actually the carbon dioxide that's in the atmosphere that traps a lot of that upwelling infrared radiation, the heat radiation, okay, and warms the planet. If it wasn't for the greenhouse effect, the Earth would be frozen solid. Okay, we would have temperatures that are about minus 15 degrees Celsius on average on the planet. So this is a very important component of the natural global system to keep the planet warm. The problem is that the amount of energy that reflects and moves out from space and the amount that's absorbed is in a very, very delicate balance. And that balance has been responsible for the climate that we've seen over the last millions of years. Subtle changes in ocean circulation, subtle changes in the amount of greenhouse gases make the system out of balance, and the system responds by either warming up or cooling down. Okay, so it's subtle changes that are going to take us out of this very, very tight balance and this dance that we've been walking with the sun and with the planet for the past 50, 100 million years, going back actually, when you think about it, back to the origin of the planet 4.5 billion years ago. It's interesting that the sun, at the very start of Earth 4.5 billion years ago, was about 75% less energetic than it is today. Yet we don't see any evidence of glaciations for almost 2 billion years on the planet. And it's not because there wasn't water, it's because we think there was a lot more greenhouse gases in the atmosphere at that time to trap more radiation to keep the planet warm even when the sun was weaker. Okay, so the distribution of heat on the planet is primarily warm in the tropics. Nothing surprising about that. Cool up to the poles. You see a very, very warm region over in the Indo-Pacific. This is where that wonderful coral reef diving is, and off of Australia and the Great Barrier Reef and in the West Pacific. All right, so what's been happening? Well, what's been happening is something that is somewhat scary, and within the next 2 years, you're going to see in the newspapers, there's going to be articles. Time magazine, I guarantee you, is going to have this. It's going to say 400 ppm, okay? 400 parts per million CO2 in the atmosphere. And the reason it's going to be a really big threshold, not because anything magical is going to happen, but the estimates are that we haven't seen 400 parts per million CO2 in the atmosphere for at least the last 5 million years. And that's a very, very scary thing because we're now approaching a CO2 level on the planet that we have not seen before. How have we gotten here? Well, we've gotten here in actually relatively fast order. This is the Mauna Loa curve, okay, that comes out of the observatory that's sitting on the island of Hawaii. And Ralph Keeling, back in 1959, had a brilliant idea saying, you know, we're burning a lot of fossil fuels. We really need to know what's happening with atmospheric CO2. And he started collecting data. And the oscillations that you're seeing around this mean is actually what's happening in the northern hemisphere. We have most of our land. Forests are growing in the summer. Forests are dropping the leaves in the winter. Every time you see the CO2 drop, it means that we're putting out new buds, we're putting out new leaves on the trees in the northern hemisphere. Every time it rises, we're going into fall and winter, and those leaves are breaking down and they're releasing CO2 due to microbial activity. So it's sort of the balance between photosynthesis and respiration as we slowly rise. Well, as you can see, we've started in 1959 at about 315 parts per million, and here we are, 2013, and we're probably going to hit that line in the next 2 to 3 years of 400 parts per million. Now, what does this look like if you put this on a longer context? Many have said that this is not due to human activity, that this is natural oscillations in the carbon system. And I think that I'm going to convince you that it's very difficult to argue this is natural when we go back even 400 or 500 years and we take a look at methane, carbon dioxide levels, and I'll show carbon dioxide in the next couple of slides, okay, going back from ice cores. Now, this is the methane record, right here that shows the rise in methane over the same period of time, the last 50 or so years, against a background of methane, which is another greenhouse gas, from the ice cores. And you can see that things were pretty stable going back prior to about maybe 1850, and the rise begins right about the time of the Industrial Revolution. Whoops, sorry, too many. All right, there's a lot of models out there. What's going to happen in the future? Truth be told, we're not sure right now. We don't know if by the year 2100, the average temperature on the planet is going to be 2 degrees warmer or 4.5 degrees warmer. And the reason we're not sure is because there's a lot of feedbacks that are operating within the system, okay, that are going to kick in as we start to slowly heat up, as the carbon dioxide and the methane build up in the atmosphere and trap a little more solar radiation and warm the planet. And the places we're going to see it first are the high latitudes, the places where there's ice. And I'd like to say that usually when we talk about climate and we talk about that delicate balance between the warming and the cooling, you look at the ice, because the ice is part of that delicate balance. If you warm up just a little, you melt a little bit of ice. So the high latitude regions are sort of the canary in the coal mine. We look up in the Arctic Ocean, and we look at this Arctic sea ice that's currently up in the covering probably about 80% of the Arctic during the summer months. And what we're finding is that the amount of Arctic sea ice has been dramatically decreasing over the last 40 years, 35 years. Now, prior to that, we really didn't see a lot of reduction in sea ice, and there were many people who asked the question, why don't we see that sea ice reduction? I mean, you've been saying that CO2 has been rising since 1800. Well, it turns out that the reason that we don't see that is primarily because of the fact that the Arctic sea ice has been thinning. So go back 50 years ago, and the Arctic sea ice on average was 2 to 3 meters thick. Today, much of that sea ice is on the order of 1 meter or less thick. Well, when sea ice is 8 feet thick, it can shrink and it can build and it can shrink and it can build on summer-winter cycles. It doesn't go anywhere. When it's only a couple of feet thick, during the summers, it can melt back completely. So what we're starting to see, here's the Arctic ice extent, and we have this natural cyclicity. And as we get into the last 8 or 10 years, we're starting to see these very large changes that are predominantly due to very large areas of ice melting back and then growing in the winter and melting and growing. The problem, when they melt back, the sun is now able to hit the surface of the water and warm it up. So every year, the Arctic Ocean just gets a tiny bit warmer, and the sea ice starts growing a tiny bit later. This becomes a major problem when we're thinking about the fact that the ice turns out to be a critical feedback, a critical component of keeping the planet cool. Many of you ski up in the Sierras. You know, you put sunblock on, you put your sunglasses on in the winter. The reason is that snow and ice reflect sunlight. The less sunlight, the less snow and ice that you have, the less ice, the more solar radiation is absorbed by the ocean. What about the Antarctic? The Antarctic's a tremendous player in this game. And when we look at the Antarctic, okay, the Antarctic is in red, we really don't see a change in sea ice. We see a large change in the sea ice in the Arctic, but virtually nothing, if anything, maybe even a little bit of growth in the Antarctic. And there's a very good reason for that. The reason is that the sea ice in the Antarctic is a seasonal phenomenon. The ice grows during the winter, it shrinks during the summer. It grows, it shrinks. This is just the natural phenomena going back and forth. The extent to which it grows and shrinks on a seasonal basis hasn't really started to change because the Southern Ocean hasn't really started to warm up that much. Okay? In contrast to what's happening up in the Arctic, where we have a semi-enclosed basin, it's really absorbing a bit of heat. Okay, so this is the seasonal dance that we see on the planet with respect to the ice. About 15 or 20 years ago, the science community was stunned when satellite images caught the Larsen ice shelf shattering and disappearing within a course of about 2 years. This is the ice shelf that's of the size, the March of the Penguins. We're talking about an ice shelf now that gets upwards of 200 feet thick. And this sits right on the Antarctic Peninsula down here, okay, the Antarctic Peninsula. And what happened was satellites began to pick up lakes sitting up on the ice shelf. This is a very large ice shelf. And those lakes would grow in the summer, freeze in the winter, grow in the summer, freeze in the winter. And enough water started to percolate down that it literally shattered the ice sheet, the sea ice, and that sea ice went out to sea. Okay, so this is a sea ice phenomena. What happens when you lose the sea ice? All these continental glaciers now begin to flow. So the sea ice is the equivalent of having the ice cubes in your drink. The sea ice melts, you don't really get sea level change. As soon as you wind up releasing the sea ice, which is buttressing the fronts of these continental glaciers, that's the equivalent of putting ice in your already filled drink, and the water level rises. So all the sea level talk that you hear about is related to continental ice. The sea ice itself is just sort of the smoking gun that's holding back that continental ice in Greenland and in many places in Antarctica. All right, so this is what's happening today. When we take a look at the planet and we now go back in time, we sort of go into the geologic record, we have to actually look at the natural cycles that are causing changes in the amount of heat striking the planet. Now, back about 100 years ago, there was a mathematician, Milutin Milankovitch, who came up with a theory. His theory was that the ice ages, basically changes in the size of ice or the amount of ice on the planet, was controlled by subtle changes in the orbit of the Earth around the sun. And today we call those the Milankovitch cycles. One of these cycles is related to the amount of tilt. So as the tilt of the Earth changes on a 41,000-year time scale, okay, the amount of sunlight that's striking the high latitudes, the Arctic, or if you'll put it around the other way, the Antarctic, if we're going around the sun, all right, is going to vary based on how direct the pole is facing the sun. This tilt is not very great. The change is about 22 to 24.5 degrees relative to the plane of the ecliptic that's going around the sun, but that 2.5 degrees can have a dramatic effect on the amount of sunlight that strikes the high latitudes. Milutin Milankovitch also talked about another type of cycle called eccentricity. Now, this one is a little more subtle. This is related to the gravitational attraction of Jupiter and Saturn on the Earth. And effectively, the Earth's orbit is an ellipse. As we remember from math, or don't remember as the case may be, okay, in an ellipse, the center is not directly in the center, but off-center at the focus, which means that the distances between the sun and the Earth vary depending on its orbit. Okay, and depending on that orbit, you can be either closer or further away. Again, affecting the amount of sunlight that's striking the planet. And when we put all this together, what we find is a natural dance of solar energy striking the planet on time scales of tens of thousands to 100,000 years. This is the natural climate cycle. Okay, and this sort of at the top, this is the 100,000-year cycle, which is eccentricity. There's this 41,000-year cycle. There's another one we call precession. And when you put all these together, what you wind up with is a dance, warming and cooling, that's driving the ice ages. The natural cycle of warming and cooling. The paleoceanography community has done a tremendous amount of work collecting data from the deep sea, and I'll show you some of that in a little bit, okay, that analyzed and basically proved that Milankovitch was correct, that the dance is driven by these tens of thousands of year cycles, which are subtle variations in the amount of sunlight that's striking the planet. The thing we didn't know was how does the greenhouse gases of CO2 and methane play into this? Are they playing at all, or are they constant and it's just sunlight that's bouncing around? And a study that came out in the late 70s, which I consider probably one of the most important suite of studies for the climate community, was a group of researchers that decided to go to the Antarctic and to work at a Russian station called Vostok, which sits right up here. So here's that peninsula that we were looking at, the Larsen Ice Shelf. Up at the top would be South America. Okay, down here would be New Zealand and Australia. Okay, so there's the Vostok station. They decided to drill a hole through the ice and to collect the ice and bring it back into the laboratory. And it's a lonely place up on the ice sheet. There's not a lot. It's a great place to play soccer in the summer. You can land planes on this ice. It's that flat. And this is the drilling station. And what the researchers were doing was going down thousands of feet into the ice. The ice here is about 4 kilometers thick, so it's 12,000 feet thick. It's a very thick ice sheet, and pulling up cores like this of pure ice from deep in the ice shelf. And why are they pulling up these cores? They're looking for that. As ice freezes, it traps gas bubbles, basically the atmosphere of times past. And it's possible to grab these ice bubbles and extract them from the ice by slicing the ice going back in time and analyze the air, the atmosphere that's trapped in the ice to figure out what the greenhouse gas concentrations were. And when researchers did this, what they discovered was something that changed everything for the climate community. So up on the top, we have carbon dioxide levels. On the bottom, we have methane levels. And what we have over here is a type of isotope called deuterium. This is effectively the type of hydrogen, or the different types of stable isotopes of hydrogen in water. And this particular stable isotope of deuterium to hydrogen varies with temperature. And what you're looking at here is the heartbeat of climate. This is the top of the core. This is the last warm period, which we're in right now. We call it the Holocene. 20,000 years ago, we were in a glacial period. 120,000 years ago, another warm period. 140,000 years ago, another glacial. 240,000 years, another warm period. And so on, going back 750,000 years. But more importantly, the CO2 record perfectly tracks climate. When it's warm, we have excess CO2 in the atmosphere. When it's really cold, we have low CO2, low greenhouse concentrations, high, low, etc. Those CO2 levels are varying for a variety of reasons that we're still trying to understand clearly, but it's related to ocean temperatures, ocean circulation, the amount of plants that are on the continents as those ice sheets move forward. Okay? But the most important thing is that excess CO2 or high levels of CO2 help to amplify and make the planet warm. Low levels of CO2 we find when the planet's cold. Now look at those numbers. Going back 800,000 years, the maximum carbon dioxide levels that we see are somewhere between 280 and 300 ppm, parts per million. A million years of climate says the natural order of things is to keep the CO2 in this very tight range of 280 to 300 and the glacial maybe 180. Where are we today? 400. When you place 400 on this plot, it's really hard. This is the Mauna Loa curve. It's really hard to argue there's something fishy going on. There's something that's not natural. This is anthropogenic production of CO2. This change right here is effectively 50 years. This is just the Mauna Loa record. So this is about 60 years of CO2 change. The magnitude of this change is equivalent to the magnitude of the CO2 changes we see as we come out of ice ages. And these transitions take somewhere on the order of 3,000 to 6,000 years. And this CO2 change we have right here is now going into the atmosphere over a 50-year period. So the rate of change is dramatic with respect to the natural order of things. It's really hard not to argue that human activity is responsible for that. Okay, we go back now. Here's the Vostok record. We can see the methane record, the exact same thing. We go back and we can see this dramatic increase in methane that starts about 1850. Kind of interesting that methane is already beginning to level out a little bit, and that has to do with production versus release versus destruction in the atmosphere. Methane only stays for about 10 years and then becomes CO2. Unfortunately, as the permafrost in the Arctic and in Canada begins to warm up and the ice begins to melt, we're going to get more methane entering the atmosphere in a short order. So we have a CO2 problem. Okay, the CO2 problem is we've put about 100 ppm extra CO2 into the atmosphere, effectively about 50% of the glacial amount, 30% of the interglacial amount in the last 50 years. But what has this done to the planet? And why should corals care what we're doing? Okay, and this is the ocean acidification problem. The best way to think about this is to think about what happens in your Coke can or your Diet Coke can or even your bubbly water, all right, when the manufacturer pumps CO2 into it. Well, when your manufacturer puts CO2 into your soda bottle, that CO2, unlike most gases, combines with the water that's in the bottle, and it makes this chemical right here, and this chemical is carbonic acid. If you look on the side of a Coke can, it says carbonic acid. That's where the carbonic acid comes from. And since we have excess CO2 that's going into the atmosphere, the ocean's just sitting there like your Coke can. It's saying, you know, I can absorb gases from the atmosphere. And since we're now getting out of equilibrium, what happens is the CO2 starts to dissolve into the ocean. About 50% of the CO2 that we've produced over the last century is now dissolved in the ocean. And that's one of the reasons atmospheric CO2 levels aren't higher. The CO2 is just a wonderful sponge for CO2. And once it dissolves in the ocean and makes carbonic acid, this carbonic acid begins to lose protons, okay, and it's a bunch of chemical reactions to get down to this bottom reaction, okay, which is a CO3 is carbonate. Well, you might know that corals make a skeleton of calcium carbonate. Corals want to be able to take the carbonate out of seawater to make their skeleton. The more carbonic acid we put into the system, the harder it is for those corals to make their skeleton. Okay, so here's kind of a quick summary. Okay, we are now putting about 2 petagrams, and petagrams are like gigatons. It's basically the exact same unit of carbon in the atmosphere, and about half is going into the ocean. And when that half goes into the ocean, what we have now is the carbonic acid that's being made, and that carbonate that's sitting in the ocean in a fixed amount, okay, is starting to neutralize this carbonic acid to make another form we call bicarbonate. And this turns out to be the same stuff that's in Tums. When you have an upset stomach, you take your sodium bicarbonate, okay, which helps to also neutralize the carbonic acid. Okay, so what we wind up with is we're using up the carbonate. And as we use the carbonate, the critters, like corals and other marine organisms that live in the ocean, have a tougher and tougher time making their calcium carbonate skeletons. Now, are they going to go extinct? Corals are not going to go extinct. They're going to maybe have a tougher time competing with organisms that do better with CO2, for instance, algae. But there are organisms up in the high latitudes in North Pacific where this could become a tremendous problem over the next 30 to 40 years as the ocean gets a little more acidic. Now, understand, the ocean is not acidic. It's not at a pH below 7. Okay, if you remember your chemistry, all right, we always talked about the fact that at pH below 7, water is acidic. At a pH above 7, it's basic. The seawater is sitting right around pH 8. We're not going into pH 6, pH 5. What we're doing is we're moving the ocean slightly in the acidic direction. It's still basic. So things are not dissolving like crazy as it would be if you took calcium carbonate or you took vinegar and you put it on your sink to get rid of the carbonate, the buildup on your sink. That's acidic. What's going to happen is these organisms are just going to have a tougher time making their skeletons. And by doing that, okay, and absorbing the carbonic acid and with the carbonate, okay, what we wind up doing It's just making these subtle changes in the pH of the surface ocean, and that's what's triggering this problem of ocean acidification of organisms that have planktonic existences, for instance, mussels and echinoderms. Many of you might probably like uni, okay, sea urchins. These are the organisms that could potentially be affected by ocean acidification. And there's a lot of research going on now to get a sense of what the effect is going to be of subtle changes in the pH of the surface ocean. All right, so now we're going to just step back in time. We're going to call it Tales of the Crypt. We go into a little bit of what I do. I work with these beautiful creatures. These guys are marine protozoa. They're called foraminifera. They live in the ocean. If you go to Catalina, you go to Bodega, and you take a plankton net, you'll find many of these species in the surface waters. The reason these are so important is not because they're plankton, but because they make tiny little calcium carbonate shells. And these calcium carbonate shells lock within the microchemistry of those shells, they lock information about the environment that they lived in when they were alive. And by teasing out the meaning of that microchemical changes, we can tell what the ocean, what climate was doing in times past. Now, the way we do this, specifically for the purposes of going back in time, okay, is to go out on a ship like the Geodi's Resolution. This is a drilling ship that is run by the National Science Foundation to collect deep sea sediments around the planet, okay, which contain the tiny shells of these planktonic foraminifera and other species that have fallen through the water column and hit the bottom of the ocean after their lives are finished. And these guys live for about a month. All right, so they lock in a very short period of time. And when you clean up the sediment, when you sieve it and you wash it, what you find are millions and millions of these tiny shells, which are on the order of a half a millimeter to a millimeter in size, in the sediment. Matter of fact, in some places in the Atlantic, the marine sediment is 90+% shells of these marine organisms. So there's a lot of calcium carbonate, there's a lot of shells falling from the surface ocean down into the seafloor and accumulating there. What do we do with it? Well, in the Stable Isotope Laboratory at UC Davis, what we do is to look at the microchemical changes that take place as we move down through these cores, okay, to reconstruct what climate is like. All right? And this is sort of a CSI geology sort of assignment. Okay, it turns out a little bit of chemistry. The oxygen, for instance, that we're made of, okay, is composed of stable isotopes, isotopes of oxygen. They're not radioactive like uranium or like carbon-14. They're stable. We're all made of oxygen-18 and oxygen-16. Same thing for carbon, carbon-13, carbon-12. These are stable isotopes of carbon, stable isotopes of oxygen. What can we do with these? Well, it turns out that because the only difference between this upper oxygen-18 and this lower oxygen-16 is the number of neutrons that it has. The protons are the same. That's what makes it an oxygen. And because this is a more massive atom than this, approximately 10% more massive, as organisms make their shells, whether it's calcium carbonate or some other type of mineral, okay, the relative proportions of the heavier and the lighter isotope change with the temperature of the ocean. Okay, the warmer the temperature, the oxygen-18 has the ability to get discriminated against in the shell, and in the laboratory, we go down to Santa Catalina Island to do this. We scuba dive for these foraminifera. We're able to look at the oxygen isotopic composition on the lower x-axis of the shells as a function of temperature, and this is a calibration we've done in the laboratory. These calibrations mean that we can reconstruct ocean temperatures in the past within about plus or minus a half degree Celsius, just by looking at the oxygen-18, oxygen-16 ratio of the shell. It's pretty phenomenal when you look at these calibrations and then you apply them in the geologic record. And the eye-opener was when we started to look at what was going on in the past. So the Geodi's Resolution takes a core. The core has a lot of fossils. in the laboratory. We put these fossils, we analyze them with a mass spectrometer, and we wind up looking at the carbon-13, carbon-12, and the O18-16 ratio, and we're able to reconstruct information about ocean temperatures and also how much ice was on the continents, as well as something about the carbon system. So what is it about the carbon system in the past that allows us to figure out what's going to happen in the future? Back about 65 million years ago, okay, for those of you who know your neighbor over at UC Berkeley, Walter Alvarez and his father were working on a fundamental question: what killed the dinosaurs? And this is a great read if anybody wants to read a good book on the story of how they figured out it was an impact. This is what the continents look like back about during the age of the dinosaurs, about 100 million years ago. And from looking at the geochemistry, the microchemistry of these fossils, we have a lot of information about what was going on in the planet over the last 65 million years since the dinosaurs went extinct. So here's 65 million years ago, the right side y-axis. And what we're looking at here now are the oxygen isotope ratios of a type of foraminifera from the deep sea. And we can see that during the early part of the last 65 million years, the deep ocean was warm. As a matter of fact, it's 12 degrees Celsius. That's Monterey in the summer. But this is the deep ocean during the early part of the Cenozoic. And then you wind up cooling down dramatically as you come towards the present, and we have Antarctica and Greenland glaciated. So why do I show this? Well, a group of researchers were working on this particular problem. When did Antarctica glaciate? How cold did it get? And at about 55 million years ago, they discovered this like blip. You can see this is just natural progression in both carbon and oxygen, and then there's this line here with all these points on it. And what they discovered was an unusual amount of carbon-13 and an unusual amount of oxygen-16 in the shells of these foraminifera. Matter of fact, the amount was so astounding that, as I like to say, they discovered something really, really scary. And what they discovered, okay, was that there was a very, very abrupt, that's the best way I can put it in chemistry and dogs. Okay, so for the canine lovers in the group. What they discovered was over a very, very short period of time. The estimates now are about 3,000 to 10,000 years. The carbon system of the ocean and the terrestrial environment changed dramatically. Matter of fact, it changed so dramatically that when we take a look, and this is on this particular scale, dead dinosaurs are on the right, okay, and humans are on the left. We're coming back in time, and you can see this very, very abrupt change in the chemistry, this very abrupt change in the chemistry. What this said was the deep ocean warmed up 5 to 6 degrees Celsius, 10 to 12 degrees Fahrenheit, on an order of less than 10,000 years. And the carbon chemistry of the ocean changed dramatically on this time scale. Now, why is that important? It's important because it's really, really hard to change the carbon chemistry of the ocean. The ocean has something on the order of 35 times more carbon in it than the atmosphere. It has about that much than the terrestrial environment. So how do you change the ocean's chemistry when the atmosphere and the terrestrial environment have really so little carbon in it relative to the ocean? And a young grad student at the University of Michigan came up with a brilliant idea. It's probably one of the most cited papers on this particular event we call the Paleocene-Eocene thermal maximum. And he went, and this is sort of Jerry Dickens, and by the way, the study of this event got, I think, there's probably 50 faculty positions around the planet just studying this one event. And this is all the different quantities of carbon that are in the atmosphere, the ocean, the land. And when you look at these, there's nothing there that will allow us to reconcile this chemical change. And Jerry's idea was that we're missing a carbon source. The carbon source we're missing is a carbon source that's sitting in marine sediments along the continental shelves, even today, and it's methane hydrate. There's a huge amount of methane hydrate that sits along the continental shelves. It's thought to be about a quarter of the amount of carbon that's in the ocean. Why is that a problem? Well, methane hydrate, what it is effectively methane gas that's caged in water molecules, and it's stable because at temperature and pressures at about 800 meters in the ocean, you can get methane hydrate. If you decrease the pressure or you increase the temperature, the methane becomes unstable. So on deck, this is on a ship, on deck they could have put a match to this and it would burn. Methane's coming off constantly. And when we look in the deep sea with submersibles, this is methane sitting on the seafloor off the coast of Monterey. Deep, thick deposits of methane that's stable because the ocean temperatures are just cool enough to keep it stable. Now, why do I talk about methane? Well, in effect, what happened 55 million years ago, okay, is we had a methane release event. The chemistry of the fossil foraminifera tells us that it was methane because it has a unique carbon-13, carbon-12 ratio. And that methane got out and went into the atmosphere. And after about a decade or so, the methane became CO2, and we start to see a big change in the chemistry of the carbon on the continents. And that CO2 dissolved in the ocean, and it mixed into the ocean, and what you wound up with is this big shift in the carbon isotopes. Now, this caused some wonderful things to happen. For instance, the tropics moved up to Montana and Canada. So the animals that were living there were just having a great time. It was raining everywhere. There was plenty of vegetation. It also did something which was the reason that the Eocene was really named, and that is it opened up land bridges between Asia and North America, and animals which couldn't survive winters at those higher latitudes could now survive it because it was warmer. And we started to get exchange of these large mammals across between Asia and between North America. And finally, things cooled down, and when everything settled, we suddenly have all new species of horses developing, all new species of terrestrial mammals developing in North America and Asia. Okay, from the ocean's point of view, it wasn't such a good thing. All right, and there was a group of researchers that went out to figure out what happened in the ocean. And they went off on a ship on the Georges Resolution off the coast of Namibia in Africa, and there's a ridge that sits out in the Atlantic Ocean, and they started drilling holes in the sediment to try to figure out what happened at various depths in the ocean 55 million years ago. And Jim Zakos and a group of researchers from Europe and around the US published this paper, and this was the real eye-opener for the community today to understand what's going to happen to the ocean ecosystems with the CO2 that we're putting out. Okay, and what they discovered in a bunch of these cores, okay, and these are different water depths. Now you're looking at something at 2,700 meters, 3,000, going down in depth. Okay, dead dinosaurs are down here. We're coming up, all this white stuff, that's calcium carbonate. The shells of fossils that are just, of organisms that are just falling to the seafloor. And then abruptly at this event, we have no calcium carbonate. We have no calcium carbonate at any of the horizons anywhere through the ocean. And when Jim Zakos and his group plotted this up with the carbon isotope, this carbon-13, carbon-12 ratios, which is on the left side, and the amount of calcium carbonate in the sediment at different depths, they saw something that was very, very scary. And what they saw was that the CO2 that was released into the ocean, when it finally mixed, made the ocean sufficiently acidic or less basic, okay, that the calcium carbonate shells sinking to the seafloor never made it. They dissolved on the way down. And you wind up with zero calcium carbonate. Now, each of these ticks that we see here is 10,000 years. So it took 10,000 years for the ocean to finally start to accumulate calcium carbonate on the seafloor 1.5 kilometers below the surface. It took 40,000 years for it to get down to 2,600 meters. It took over 100,000 years to get it down to 3.5 kilometers. In effect, the release of CO2 had an effect on the ocean for over 100,000 years. That's what the geochemistry tells us. I'm getting close to finishing. Okay, so 55 million years ago, we have a CO2 release event. That CO2 release event causes ocean acidification, and we see it in the geologic record. Why is it scary? Because that CO2 release event happened over a 3,000 to 8,000 year period. This CO2 release event is going to happen over 200 years. The rate of CO2 that's going into the system cannot be accommodated by the ocean or by the other systems on the planet. We're going to build up CO2. And the estimates are, very scary way, that the atmospheric CO2 from the models, based on the studies from 55 million years ago, suggest that we could get to CO2 levels we haven't seen since the dinosaur age, 2,000 parts per million. Now remember, the carbon dioxide levels in the atmosphere, okay, are going to trap more infrared, trap more solar radiation, and we're going to get further and further out of that sort of balance between what's coming down and what's reflecting back into space. All right, so just the latter part of this, how do we really know humans are involved? Okay, well, it turns out that there is a CSI forensics team that's been working on looking at the types of carbon that have been going into coral reefs and other marine organisms over the last 100 years. I say CSI forensic because this really is a forensic story. We know that over the last 150 years, CO2 levels have been rising from about 290 to about 350 parts per million, and now up to almost 400 parts per million. The unique aspect about the carbon that's going in the atmosphere is that the CO2 can have different ratios of carbon-13 and carbon-12. We know what the atmosphere's ratio is. Okay, I'm going to give you some numbers so you understand it. The atmosphere ratio gives us a value of -7 per mil. The ocean's about 0 per mil. Okay? When we burn fossil fuels, we're effectively burning plant material that existed in times past. The plants discriminate against carbon-13. It has a much less carbon-13. It turns out the delta C13 value is about -25 per mil for fossil fuel burning. What do you expect to see? Well, when you look at the carbon-13, carbon-12 ratio, what you see is a record of these more negative values mean that we have less carbon-13. It effectively has to be due to burning of organic matter. The carbon isotopes don't lie. And not only that, and this is not something to worry about, okay, but it's something that is measurable. As we know, plants photosynthesize, they make oxygen. The fossil fuels we're burning today is the photosynthesis that occurred over the last 400 million years. As that photosynthesis occurs, plants produce oxygen. So as we burn fossil fuels, you can actually measure the carbon dioxide, the oxygen levels on the atmosphere dropping now. Now, don't worry, we're not going to suffocate. There's plenty of oxygen. But it is measurable now, the decrease in oxygen levels, and that has to be due to burning, okay, of fossil fuels. All right, so let me finish up with two last slides. Okay, and the take-home message. From the science, the consequences of increasing greenhouse gases on the Earth atmosphere climate system, it's not fiction. We can look into the fossil record, we can see events that have occurred, and we can quantify the effects on the ocean atmosphere system. The chemistry and the science behind these issues are the result of careful research. This is not a group of scientists that are trying to pad their wallet and just get more money into the laboratory. We have spent decades of research trying to make sure that we are as careful as possible about our interpretations based on calibration experiments like I showed you from my laboratory, done on living foraminifera that represent the fossils or very similar to the fossils that wind up into the marine sediments. This CO2 can have a dramatically long-lasting effect on our oceans and our ecosystems. It takes a long time to get the CO2 out of the system. Okay? It's not something where the CO2 is simply going to disappear. As a matter of fact, during the Paleocene-Eocene thermal maximum, it took 100,000 years for that CO2 release event to basically get neutralized in the ocean. How much CO2 was released during that PETM event? 3,000 to 5,000 gigatons of carbon. That's about what's estimated if we burn fossil fuels at the rate we're burning to the point where we run out. It's about the same magnitude. And on this is, I think, is probably the most important aspect This is a multi-generational problem. Politicians and society is not equipped to deal with this. And this is where the scary part comes in. Okay? These require out-of-the-box solutions. We have to be realistic. We can't turn off the carbon tap. You've heard we're addicted to carbon. We're addicted to fossil fuels. The reality is there are no substitutes for aircraft. We're going to have to burn fossil fuels if we want to keep flying. Cars, we can get much more efficient. It's going to take 50 years or 60 years to switch the country over from a carbon footing to some other renewable resource. It just can't happen instantly, which means that the government has to step in and has to develop a coherent energy policy that involves renewable energy. That's the only way we get off of this problem. Okay? So when we think about the climate problem and we think about what we're doing, that's us, and that's the climate, the CO2 system. And we've been tickling it for an awful long time. Okay? What's going to happen over the next 50 or 100 years is not anybody's guess. We have a pretty good idea what's going to happen. And the scientific community is very concerned that we are getting very, very close to that threshold where the best we can do is to try to adapt. We won't be able to mitigate. Okay, so this is the science of climate change. This is the background, and this is how we are very confident that human activity is responsible for the excess CO2 and also for the warming that we're starting to see. And I, as one, feel that the models are now pretty accurate, that we are going to see something on the order of a 2 to 3 degree average global warming on the planet over the next century. We've moved so far along this path, it's really hard right now to simply turn it off, and we're losing time. So for those of you who are taking the classes here, this is something that you have to deal with and become proactive. Okay? You can't be passive about this problem. The longer that the college generation is passive, the deeper the problem is going to get. The rest of us out here, we're a bunch of old gummers with our houses and our mortgages, and we're trying to figure out how to get our students through college, our children through college. It's really tough to say, we're going to take a major hit to the standard of living because many of us are just trying to make it and make ends meet and get by. Okay, and this has to come out of the youth generation today. So be proactive. Do not let this be passive. Okay, this is a problem, and we have to deal with it as a country. So I think I'll stop with that and welcome any questions. So thanks a lot.